In this video, we're going to go over some cautions about correlation and regression. Last chapter, we mentioned 3 cautions about regression. First, correlation, R-squared, and the LSRL should be interpreted for linear relationships only. Second, R and LSRL are not resistant to outliers. Third, extrapolation, which is predicting outside the domain of observed x values, is dangerous. Don't do it. We want to avoid it when we're doing our interpretation. Here is a fourth. Beware of averaging. Consider the scenarios in here. We are doing the days of school year and the altitude, which is also known as the happiness score, the relationship between these two. We're trying to find, is there a relationship or a correlation with these two data, these two variables. And as you can see, the green dots has R with 0.8, and the red dots has R with 0.95. We're losing variability when using averages. So we really want to see each day's happiness score based on this graph. But after averaging them, you can see the overall relationship becomes more clear. It becomes a upward straight line. But that's not the thing that we want to analyze right here. What we want to try to focus on is the happiness for each day of a school year. So if we averaging them all the way, we might lose some variability. Because think about that. You may have different mood in the morning versus in the afternoon. We cannot guarantee we have the same mood all day long. So it's dangerous if we average the scores right here and just make them a straight line. It's good if we really want to see a general picture, but if we want to zoom in closely, it's not a good idea. So keep that in mind. And a fifth, there are 3 possible types of relationships in your scatter plot, and 2 of them are hidden, so be careful. The 3 possible types of relationship is cause. Think about the following scenarios: diet, metabolism, and genetics. If we want to analyze the relationship between BMI of the daughters and the BMI of the mothers, after we analyze those data and we plot that into the graph, we get seems pretty positive and linear relationship, and also strong. We get an R value of 0.506. I mean, not so strong, but moderate. So you may want to draw the conclusion right away, but what are some misconceptions, or what are some hidden reasons that we may forget? Well, ages is a thing, because we didn't say any of the prerequisites of the daughters, like what is the average body situation of the daughters, what are the average ages, because, like, young child, maybe they're in growing ages, they tend to eat more compared to their mothers, which is fully adult women, most of the cases. So that may lead to some bias and some misconception, which will draw a wrong direction for our data. And that's the thing that we want to avoid. And this is another example we went over in class. But just to give you a general idea of what a bias will be like, even though the statistics give you a pretty reasonable graph or conclusion, you cannot draw that conclusion right away because you may forgot something that will lead to bias. So there's some cautions. Controlled experiment will lead to causation. Otherwise, we cannot guarantee for any cause relationships. So what I mean by that is you cannot say because A happens, that causes B to happen. We only can say it that way if we have a controlled experiment. Otherwise, we cannot. So be aware of some lurking variables. What is the lurking variable? It's a variable that is not x or y that may impact the relationship between x and y. So it's like a third person that out of the circle, but it will impact both x and y, or the relationship between these two. So think about a scenario right here. Number of visitors to the doctor, or to the dentist, and versus the amount of ice cream consumed. we want to see if there's any relationship between these two events. And after a data collection, we got a moderate negative relationship between these two. So can we draw the conclusion right away? Well, we cannot, because you may think eating more ice cream will reduce the number of times you visit the doctor or dentist. And maybe you'll see eating more ice cream will make people more healthy. That's not the case, or that's pretty counterintuitive. Because we forget something. We forget some lurking variables that exist in the situation, which is the time of the year. Because in different times of years, in the summer, if people tend to eat more ice cream, that has no relationship with people who eat ice creams and have more healthy body. Because in the winter, people eat more ice cream, that will actually lead to more possibility that that person went to see the doctor. So the time of the year really impact how we look at the question. And here are some other, here's another blank graph for you to do it by yourself to imagine that a little bit. Also, some common response is another causation. So think about the scenario right here. Freshman year GPA versus SAT scores. And the freshman year, I mean the freshman year in college. So as you can see that there's a positive, linear, strong relationship between these two events. So can we draw the conclusion right away? Well, maybe not. Think about it in this way. Students have higher GPA in college. Most of them, we will assume that they tend to keep their performance all the way up. Like along the way, they are doing their job very good. So students who get into more prestigious colleges will have higher SAT scores, right? So that will lead to a bias, because if you only do an experiment in a specific college and you get the data from that college and you use that data to predict the overall performance of the students nationwide, that won't work, because different colleges have different entrance requirements for students. So students gets to Ivy League compared to a community college, they will probably have like pretty different SAT scores. So we cannot say that students have higher freshman GPAs leads to higher SAT scores. That does not matches our intuition. So that's an example for a common response. Another example will be GPA versus ability, or SAT versus ability, if you want to think deeper into that. And lifespan versus religious activity. This is another scenario we want to focus on. And that leads to another causation, which is confounding variables. After collecting the data, you can see that lifespan and religious activity seems having a positive, linear, strong relationship. But can we draw the conclusion right away that lifespan leads to, religious activity leads to longer lifespan? Well, maybe not, because people who having religious activity every day maybe tends to keep a more healthier living style. I don't know, but that's really a thing that we want to focus on, because the confounding variable may also draw bias in our conclusion. The effects can be distinguished from one another, or it's some possible variables that will lead to a wrong conclusion. So here are some examples that I hope give you a good idea about what the causations will be when we are doing our examinations and draw conclusions. And just keep that in mind whenever you're facing a situation or a FRQ. If they're asking you draw the conclusion, think about what are some potential risks or potential bias that will make your conclusion deviate from the real truth.